This lesson is IB 22, D and E, and this is D, and the topic is Table of Outcomes. And these tables are used for categorical data, like this one, child versus adult, child and adult versus whether they liked or disliked the ride. And so somebody took a survey, and here were the results that they got. And then we're going to be asked to find some various probabilities. In order to find the probabilities, we have to sum these columns and these rows. So if we sum this one, we're going to, so these are the totals, 72, this one's 58. Then summing this one, we're going to get 83, and this one will be 47. And then you also want to sum your both of these and make sure you get the same value, 130 in this case. Now that after you find all those sums, you can answer the probability questions, which are, first of all, find the probability that a randomly selected person liked the ride. So probability they liked it. I'm just going to abbreviate liked. So this one's fairly simple. You just find all the people who liked the ride. That would be 83 of them out of the total of 130. And I don't think that reduces, so we can just leave it. Or you can divide it and get a decimal if you prefer. I'm not sure if the IB cares one way or the other, or whether they want a decimal or a fraction. You could divide that on your own if you want. Okay, let's do the next one. Letter B. Probability the person is a child and disliked the ride. So that one's not too interesting. You just find the children that disliked the ride. There were 17 of them out of 130. So that one's pretty straightforward. Okay, next one. Probability adult. The person is adult or they disliked the ride. Now this one gets more interesting. So we have ors are where you take all the adults along with all the people who disliked and you add them up. So all the adults there were 58 of them out of 130, plus all the people who disliked the ride. All the people who disliked them were 47 out of 130. Now, if you don't like that, there's a reason, because you have a good intuition. We can't actually stop here. And the reason is, when I added up all these adults, and then I added up all the ones who disliked the ride, I added these adults that disliked the ride twice, didn't I? This 30 was included in this sum and in this sum. We don't want to count these 30 people twice, so we actually have to subtract the overlap, as I like to call it. Those 30 people have to be subtracted out. So, to save time, I worked this ahead of time, just double checking my math here, and I got 75 out of 130. Now I'm guessing this book, since I have not worked through it before, but I'm guessing they're going to tell you what this formula is. I'm just going to go ahead and tell you it right now. Whenever you're finding the probability of A or B, you find the probability of A, that was this one, plus the probability of B, which was this one, minus the overlap, which is also called the intersection, probability of A and B, or the probability of A intersect B. So from set theory, you've probably seen this before in your prior classes. This means intersect. So this means A and B right here, which was what the 30 was. So that's kind of fun. Letter D. Let me look and see what that one was. Oh yes, that one's interesting as well. New color. Letter D. Probability. They liked the ride given that person was a child. Now, you can write it like this, given child. I'm just abbreviating. Now, another way you can write this is probability they liked the ride given they were a child. This vertical bar means given. Then it saves time writing it out. So what you have to do on that one, you probably have an intuition for that one. You find all the children, so there's 72 children, and out of those 72, 55 of them liked the ride. So it's going to be 55 out of 72. Okay, letter E. So that one was, oh, another one. E, oh, running out of room. I'll put it up here. Probability, the person is an adult, given that he or she disliked. So given they disliked. So we look at all the ones who've disliked. That's this way. And out of those, 30 of those were adults. So that's 30 out of 47 is your probability for that one. So that's all D. That's the only example for letter D, section D. So we're moving on to E. E is on compound events. Independent versus dependent. Independent events are when the occurrence of one event does not affect the occurrence of another. I want to make sure I'm using the right word. Sorry. Okay, occurrence of one event does not affect the other. Whereas with dependent, they would affect each other. So that's the occurrence of one event does affect the next one. Occurrence of the first event affects the second or the following events. Can you think of some examples? Well, I can. Drawing marbles out of a bag without replacement. So drawing without replacement. Because if you draw a marble out and you keep it out, it's going to change the probability of your next draw. What else? That's a good one. That's the one that just comes to mind. Dependent. Maybe you can think of some others. I know there's plenty of them out there. So let's see. I just need to look at my notes and make sure I'm not skipping anything. Oh, let's talk about examples. So this was an example of a dependent event. I did not mention an example of an independent. An independent one would be something that's like completely unrelated. Like say you toss a coin and then you roll a die. Or how about even rolling a die twice? Is the outcome of the first roll going to affect the outcome of the second roll? No, because it's the same die and it has has a fresh probability every time. So, or rolling a die twice. Those are independent events. So, example, just make up an example here. Let's say you are tossing a coin and then rolling a die. Toss a coin, then roll a die. Find the probability that you get tails, then roll a 6. Well, all you have to do is use the multiplication rule. You're going to find the probability of tails times the probability of rolling a 6, which is 1/6. Whoops, that's not what I meant to write. I meant to write rolling a 6 there. Rolling. So the probability of getting tails if you toss one coin is 1/2. Probability of rolling a 6 if you roll one die is 1/6. And you multiply those together and get 1/12. So if you're doing independent events, something and then something else and something else, you would multiply those probabilities together as long as it's independent. Let's talk dependent. Dependent events, same deal. The probabilities, you would calculate the probabilities the same way. So this is for dependent. the probability of A and B, you would still find the probability of A, and you would still multiply the probability of B. However, the probability would be the probability of B given that A occurred. Or in other words, another way to write it would be probability of A times the probability of B given A. So that's a more succinct way of writing it. Same rule, same multiplication rule. You're just thinking about it a little bit differently. So let's do a couple of examples out of the book, because they have nice ones that I like. So let's do example 9 and 10. We have a box that has 4 red tickets, or whatever you want to call them, okay, marbles, tickets, and 2 yellows. And we are going to randomly select tickets without replacement. 2 tickets, okay. So we're going to select 2 tickets without replacement. Find the probability, so this is letter A, that you get 2 reds. Both are red. So that means the probability that, so you're going to be multiplying these 2 together. The first one you're going to multiply, so what's the chance the first one is red? 4 out of 6. Times, what's the chance the next one is red? Well, since you're not replacing, there's no longer, you've already taken one of the reds out, so there's only 3 reds left, and there's only 5 tickets left. Now at this point you can simplify, and 2 goes in there, so 2/5. Next, probability. The first is red and the second is yellow, so the order matters. A red, then a yellow. So the first one is red, that's still going to be 4 out of 6 because we're back to the beginning. And then the second one is yellow. Well, there's still 2 yellows left, but there's now only 5 total. So I can cancel, and nothing else cancels, so multiply across and we get 4/15. Example 10. This one's a little more exciting. This one you have 20 tickets numbered 1 to 20. And we're going to draw 3 tickets without replacement. Find the probability they're all prime. Probability all 3 are prime. Well, first of all, it might be a good idea to figure out which ones are prime. So let's make a list. I'll make it up here. Is 1 prime? No, it is not. So, and I was going to think about why that is. There is an explanation for that, and I think it has to do with the fact that the definition of prime is the only factors are 1 and itself, whereas 1 and itself are the same number, so they don't consider that to be prime. I think that might be why. And there might be other explanations as well as to why 1 is not considered to be prime. 2 is prime. 3, 5, 7, 8, 9, 10, 11, 13, 17, and 19. So those are your primes. Okay, the chance the first one is prime. Let's see, there's 1, 2, 3, 4, 5, 6, 7, 8 of those out of 20. Now, we took the first one out, which was prime, so there's only 7 left, and there's only 19 total tickets left. And then there's 6 primes left and 18 tickets left. To simplify this, because we do like to have our answers reduced, it is advisable to do some canceling before you go on. 6 and 18, that reduces to 1/3. 8 and 20, that reduces, divide by 4. And nothing else seems to reduce. So 2 times 7 is 14. 5 times 3 is 15 times 19, and I worked this out ahead of time somewhere. I got 285 when I did that. And just for fun, I have the decimal here too. It was 0.0491. Pretty low chance that you're going to get 3 primes in a row. That's it for 22, whatever that was, E already. We're cruising right along.